to give this again. They recorded. Some people are going to be watching it after fact, and we usually have a few questions at the end, and that we will say. I'm going to remind everybody if you can mute your microphone, and sometimes people cannot mute their microphone, but then maybe they could just try and put something over it because we can usually hear it. And I think we can go ahead and get started.
Great, Fiamma. Thanks very much for the introduction, and hopefully everybody can hear me. If click one of your buttons here. If you can't hear me quite right, I'll try to adjust to that. So I'm a scientist in the physical oceanography department at the Oceanographic Institution, and I'm glad to have this opportunity to talk to you today. I mean, it's a lot of fun to have this new technology to be able to reach out to people in Europe, throughout North America, wherever else you might be in the world. You might be on YouTube, and another fun wrinkle about this, that not just to everybody now, but to people in the future. So that's neat. Let's see. I want to give you the goal I have here today. And okay, I start slides here. So the goal is to give an overview of glacial Atlantic meridional overturning circulation, and go out to YouTube and a pretty broad audience. Really, who I'm pitching this to, it's in the postdocs of the Atlantic Virtual Institute, and most of you have a physical oceanography background, or at least you're physical oceanography right now. So that's my intended audience. And because you have a physical oceanography background, I'm going to try to draw parallels between physical and paleoceanography. Try to show you that the two are that different. To cover some ground here, I'm actually to assume that some of the basic principles of physical oceanography are known. I will read them quickly for everybody's benefit. And I assume that that paleoceanography is something new for everybody. Okay, second is going okay sound-wise. Let's see.
Yeah.
Okay, great. Thanks, Fiamma. Going to be an overview of the topic. Here is that it's not going to be a complete description of everything that's known. It's not going to even offer proportion attention to all the different things that are being done. And basically, not just an overview, but I drill down and give you some more detail on certain topics, where a lot of the interesting details are. For that reason, I'm highlighting some of my work as well in here. So clearly, this talk will be prospective and does not really reflect everyone's view. Okay. Glacial AMOC, or Atlantic Meridional Overturning Circulation. And I'll define what I mean by glacial here. Equal times really exist over the entire Pleistocene. So over the last 3 years or so, there's been advance in retreats of ice. But it's a little bit practical today. I'm going to focus on the last glacial maximum. And here's a plot. Two views of the northern hemisphere that hopefully you can see. Outside, it's labeled Pleistocene, but this is a snapshot from 18,000 years ago. And what you see is that glacial ice, in particular ice, advanced from the modern day, which is in contrast on the right-hand side. So here in Woods Hole, we're a kilometer or of ice at about 18,000 years ago. Note that sea ice was really expanded, and as we talk about the AMOC here today, I'm also going to play a very relevant role. this is an overview of the last glacial maximum. That's defined to be the time where the sheets, the land ice sheets, were at maximum on a global average. And currently, sea level was at its lowest stand or at its lowest value. And that was where between, say, 8,000 to 24,000 years ago. Slide. Information about the last glacial maximum. Okay, as you can panel, actually a plot taken from a 2009 review paper in Science by Clark et al. And there were different ice that had grown, especially over North America. You see IS for the Great Low-Tide Ice Sheet, even CIS on the west side of North America. That's the Cordilleran Ice Sheet, essentially mountain glaciers that agglomerated and grew together. That's the last glacial maximum here. Well, there's really two reasons. One, it's a time at which Earth's climate was very different than today. As you can imagine, it changed atmospheric circulation, sea was much different, and the world is a colder place. That's the reason why I picked the last glacial maximum is shown inside. And there are measures for different observations in which it's easy to pick out the glacial maximum. So, and there we have three different examples on the right-hand side, A, B, and C. And the bending, that's the band that's on the right-hand side, is there to be the glacial maximum as by the relative sea level, the sea level. The gray bar, left-hand, that's back at about 30,000 years ago. That's the Earth in which the sea level started falling to the EM, or last glacial maximum, low stand. And that's to the times when the local last glacial maximum occurred. So there's variability here. Not that all glaciers throughout the planet were at their maximum at the same time. And for them to find a local last glacial maximum when the glaciers or ice sheets were at that maximum. And the two here by about 10,000 years ago. Okay, what are these that we have? Panel A shows relative sea level data translated in terms of an oxygen-18 isotope ratio. So we see axis on the left-hand side. It has the O18 and W standing for seawater in this case. I'll explain what these isotope ratios are in a couple of pictures in a second. But let's think of this as relative sea level. And these correspond to a sea level about 130 meters lower than the modern day. Panel B, we have Pan-Atlantic oxygen isotope ratios from foraminifera. I'll find what that will come up in a couple of slides as well. But these please fossils found in the sea floor, that's what the water conditions were at the sea floor itself. And they set these values, O18C for calcite, which is an axis on the right-hand side, values at about maybe 19,000 years. The last glacial maximum is a red estimated by using expecting what's in panel A from panel B and expecting a temperature signal. And its temperatures were lowest right at the end of the last glacial maximum. And that change from the modern day was pretty hefty, something like 3 degrees Celsius. Okay, I'll move on. Okay, but this, I'll give you what models say about happening during the last glacial maximum. Okay, hold up here is the Paleomit Modeling Intercomparison Project, or PMIP, and it's from the citations Weber et al. 2007. And we want to make predictions about the future state of the MO, meridional overturning circulation, and that's obviously going to require a model. So present and past MOC and correct modeling, I think, was it to this goal. So he test of how at least how coherent the signal is from many different climate models. So each on this diagram corresponds to climate models run by a different agency. Not all of them are from the U.S. Some are from Europe as well. There's one from Japan. And what we can just look at the left-hand axis, and that's the AMOC strength. That'll be defined as the maximum stream function of AMOC. Hopefully it's been defined in one of your 3 or 4 previous NAVIS tests. And that is that models predict strength was stronger, that the AMOC was stronger during the last glacial maximum, or that it was weaker, and one didn't really much. There's consensus from about the AMOC strength was like during the glacial maximum. Need to clear. Up in the title, it says LGM minus PI, and P in this case means pre-industrial. Of course, do essentially 1800 or 1850, and that, for the purposes of this talk, to be the modern day. So we're looking at maximum minus the modern day. We have a second axis on here. It's the Atlantic density contrast. And the relation between this AMOC strength and the Atlantic density contrast was the largest found in this PMIT project. This was PMIT version 2. There's quite a cloud of data here. We don't see a strong, say, line coming of this. Trend for having Atlantic density contrast, this being defined as the difference in density between bottom water and north deep water, enhanced AMOC strength. So you might see some kind of thermal forcing in this. Okay, it's still a correlation coefficient, and if you look at 6 other tricks, as was done in this paper, what's that the PMIT models do not agree, say, on the quadrant of change between and the last glacial maximum. No simple dynamical rules that came out of this particular study, and that would just be like that models are inaccurate.
Ask a question?
Yeah.
So how are you running these LGM simulations in terms of forms or initial conditions or so on?
Okay, Yama. So basically what they're doing is that they are taking an estimate of what the ice sheets were like during glacial maximum. I believe it's one of PA's reconstructions. They're changing that we have the Earth in a different, essentially, different orbital sea opt, but then a coupled ocean atmosphere model as they can. I don't think it comes into equilibrium because they can only run it for, say, a couple hundred years. And the initial conditions go, don't know, say for the initial conditions of the ocean, I don't know what the answer is to that one. May have said for modern day conditions, but have to look up to see for sure. So it's essentially the forcing is supposedly what is driving the differences here in between the modern day and glacial times. That answer?
I mute myself between. Yeah, that was great.
Okay, fantastic. This is a paper from 2007. It's PMIT 2. They had work done after that on PMIT 3, by Hargraves et al. In Climate of the Past discussions. And there are things that coupled models do well. They scale SST change in a way that seems good with what we know from data. They get the length right. CI change seems to also be right on the large scales. That goes with the SST. So those two. So a lot of change. It's ocean component models that also does a good job reproducing where this oceanic convection occurs, and basically right off of the sea ice edge. So there are things that these do well, but overall, let's say the subsurface ocean, we're getting an honest picture from these models about what was happening during glacial time. Up in what I'm going to concentrate on for the majority of this talk is observations. And in particular, I'd like you to take away from this is that basically some of the tools that we can use for glacial times, and they're similar to what's being used in physical oceanography. Line paleodynamical method to kind of analogy with the red array and the upcoming OSNAP project. Protactinium rates and how they have been put forward kind of a magic bullet to give us AMOC in the past. AMOC from property distributions, which is in the best way, or the way that has the most information, and do things about rate constraints. Get information about the past ocean. Records, for the most part, consist of collecting sediments. Where in the left-hand panel is a device up on the deck ship. Collected actually the mud or sediment of fossils that are found in sediment. There's a foraminifera here, which has been an animal that lives in the upper 100 meters or so of the ocean, or it goes along the floor. So those that are in the upper ocean are called plectic foraminifera. Those that are on the seafloor are benthic foraminifera. And the foraminifera, or forams for short, are mimic, and they reflect the water conditions in which they lived, and they do that perfectly. So there can be a form of information for what the seawater was like in the past. There's a long core. This is actually ice that was developed in Seoul in order to take cores, bring them back up, and be able to either things at higher resolution or go back into the past and emulate on the floor. Basically, on one of these sediment cores will be taking you farther and farther back into the past. For the sake of this talk, we're talking about the last maximum, and we're just taking out one slice of these cores to examine. One here is that there's a difference between coring and drilling. It occurs on a drill ship where you actually provide some power to drill down into the floor, and cores are really operated by it. And mostly about infrared cores because they can use pretty high resolution. At the AMOC, one rate starting would be we could actually what the currents were like in the past. So the question is, can we directly measure currents from the past? Current meter, it's called Searle silts. And right-hand side here is the mean size, and it might be a little bit hard for you to see what's there, but this is how coarse the material is in the sediment core. Top of the lines, we have a trace going down. The top is going to be the top of the core, so that's going to be modern day. And go down here, that means going back in the past. And there are a couple of different events that are labeled, kind of blurred right-hand side, but you can see LGM is one of the lower bands on both sides. This changes in this grain size, and it appeared to occur at the same time as some of the changes in the left-hand panel. And the left panel is the carbon-13 to carbon-12 ratio, basically telling us, for the sake of just something about the chemistry of the shells. We have something else on the left-hand side being equal to something about the size of grains in the core. And these are two independent pieces of information that are telling us somewhat similar, but gives a sense that there might be a paleo. However, there's a caveat here. One of the, it's unclear this might respond to. So, look even a step back for that. Why might grain size have anything to do with currents? Because a large grain size, we need a greater current to pick it up, or more energy to pick it up. So this is basic sediment transport theory. Okay, and actually large grain size in a particular core, that's actually a deceleration of the velocity because it's off sediment. It means whatever is loaded up in the water is dropping out. So things. One, there have been greater currents, larger grain size. There must have been someplace upstream that had a large amount of energy or stronger currents, and then currents are slowing down as they pass over the core site. Okay, and that we only cores along the sea floor. It's unclear over what depth of the bottom ocean this sediment drop out of, so that's a problem. More than that, it's pretty calibrated this data with any in situ data. For that reason, and these records, I'm not going to turn to this type of data in this talk, but you know that it's out there and that maybe in the future is usable for AMODs. Okay, what's better than that is actually get velocity through the sort of, which is kind of paleomorphing. Is there a way to get density? So what we do in physical oceanography, if we can get the density field, then step closer to getting a velocity field. Okay, in order, I'd like to give you a little bit more background and to better define what I mean isotope or an isotope tracer. So here, delta 18 in the title, which is going oxygen 18 to oxygen 16 ratio in water. So we have O 18 and we have H2O 16 in a per mil notation. So it looks like a percent sign, but it's 2 zeros down at the bottom. That's per mil times, that's called parts per thousand. So a year or a notation that is defined around some kind of mean value. This mean is defined to be standard mean ocean water. I have an ocean here, that little blue square, 0 per mil on it. So everything on its own, that's our standard. Now, and precipitation occurs. Well, precipitation tends to pick up the light isotope. Oxygen 16 actually is lighter than oxygen 18, so it differentially goes up. That means it goes up into clouds. That means of oxygen 18 to oxygen 16 goes in that case. And we see the cloud has it labeled -10 per mil. That's our percent. Have a rate 1% less than ocean, or 10 mil would be equivalent. As water travels through the atmosphere, there's a process of distillation there. Essentially, that one precipitation occurs that the heavier isotope is the first one to go. That further make the isotope ratio more skewed towards 16. The delta 18 value becomes even lower or more depleted. So it's 20 per mil as we move through the clouds. Okay, now notice we have a tracer here that's behaving somewhat like salinity does. Okay, affected by evaporation and precipitation. And so, if I step forward one slide, what if we had some of this stuff raining out on an ice sheet made of precipitation of some type? you go way up to high latitudes, the O18 of the water might be even lower, minus 30 per mil. And for that, ice sheets are going to have a very low delta value. If there's, and if that water is locked up on land, that means the O18 of seawater is going to rise. So we're basically on the conservation principle here of the total amount of O18. In the last glacial maximum, the O value of the ocean was more like 1 per mil, and that's an indication of sea level change. In the cores, what we actually have observations of is this given by a little arrow down at the bottom of the ocean. This is synchronate. That's what this is a 4 made of. And record the O18 of seawater. But they record the also temperature at which the shells were made. So a function of temperature, F on there. And that takes up the value definitely in the shells. What's being recovered in fossils and sediment cores is some accurate measure of the O18 of seawater and the temperature of the past. Okay. Now the task is I don't know, what's the hydrography of the past? What are the temperature and salinity distributions like? Plotted in is the modern hydrography, and we have black dots on there. That's just the major water masses of the world ocean, as we're on the temperature salinity diagram. And the right-hand corner of that, we have Atlantic deep water, and there's a line connecting it all the way across and fresh waters, Arctic bottom water. And then we have a Y shape going up above. Yeah, this is where YouTube and webinars will have to use imagination a little bit. But the Y there is going to be more intermediate waters or Pacific waters. What basic quantity do we know when it comes to temperature and salinity? The reason we're getting after this temperature and salinity is because ultimately, if we had both of them, we'd be able to get at the density. So that's taking time to do this. Ultimately, the density would get at the AMOC. Okay, I told you that what's recorded in shells is just the O18 seawater and the temperature. Additional measurement, this is called a core water measurement, and Adkins et al. Actually, what that is squeezing out all of the water of the core. That is that the core material cannot be reused. It takes a lot of water to do this. Recovered from that is the actual O18 of the seawater. That's down in the sediment. Under this is that it's essentially a borehole problem. There were some diffusion of waters up and down through this core, and that has to be accounted for. O18 of seawater, and you have O18 of calcite or calcium carbonate shells, then the difference two is due to a temperature effect. Okay, so now extract temperature in the past. Okay, core waters contain, you can get salinity out of them, or get a measure of the salinity. So now we have both the salinity and the temperature, and we can make a map of glacial hydrography as done in the second panel here. This is the 4 dots are on there. Those that are black dots that have error bars. They are fine. So these are 4 points of deep ocean. They primarily don't change much in temperature. All of the glacial ocean was near freezing, but that salinity instead varied and caused the stratification in the glacial ocean. Pretty low at the 4 points, and not going to be able to do much physical photography. That the main problem is just it's very hard to make these measurements, and rarely the measurements come out with large error bars, mostly due to this Bohr inverse problem. So glacial hydrography, it's not going to be good enough to get the AMOC at this point. Okay, this is going to be the glacial problem, and I've picked a study here where we zoom in at the glacial Florida current and the lines on the continental, on the shelf break, and every above the shelf break is going to be dry land at this point. The current is going to be even more constrained between Florida and the Bahamas. Okay, in this sample method, I'd like to make the analogy here with rapid or O-snap. So take note, black dots, they're on both sides of the Florida current, and then we have sediment cores. Okay, moving on. Lines of argument here that will convince you that oxygen isotope ratios can density like tracer. Okay. Is oxygen isotopes of calcite? It's both temperature and the OH of seawater. Now, the OH water is a salinity-like variable because it's affected by evaporation and precipitation. Subtropics, today at least, OH has a linear relationship with salinity. Thus, if brave, we can solve for salinity given the of seawater. So that means the OH in shells, function of temperature and the OH of seawater, can be transformed into a function of temperature and salinity. It turns out coefficients for the OH, the coefficients, say, of temperature and salinity, are similar to those in a rise density equation. That's the S diagram that I've plotted up here, where these are isopycnals, there's the T lines for the physical curves here, and the dashed lines are the constant O18 of calcite lines. And to have a that's not terribly different, at least we could say. Okay, on some information, and then that's given by the shading here. In the Florida Strait, there's some correlation between temperature and salinity. The two don't dependently. We're now down the region over which, and in these smaller regions, knowledge of O18 of calcite can get a pretty good estimate of what the density is. Okay, if we have cores on both sides of the Florida Straits, then we have some estimate of density, and we use thermal wind to produce what the velocity shear is through that region. Note here, think of data as being quite restrictive, not full because it's along the seafloor. The thermal wind balance or geostrophic balance that we're after is actually the endpoints or the boundaries that matter to give us the net transport or net through transect. So in this case, data are in exactly the right place. Okay, let's give an estimate of what the glacial circulation looked like. This is from Stiglitz et al. In 1999. The top shows how the isopycnal slope through the Florida Strait today, with Florida on the left and the Bahamas on the right. That we have water banked on the right side. We have dense water banked up on the floor. If you look at calcite during the Holocene, so this is the top of the cores, which is most representative of the modern day. This slope looks reminiscent of the pycnal slopes in panel A. So in other words, panel A and panel B seem to show the same slopes. That this OH density-like tracer is working okay. Now last glacial maximum, and we see these slopes as does by a few points by the holes along the water interface, and which we can construct loops. If we interpret those as density, what it means is that the density gradient across the Florida was less during the last glacial maximum, with thermal wind balance, which hopefully recovered in pieces or one of the last few cents. That means less of a horizontal density gradient corresponds to less of a vertical shear. The assumption that the flow at the bottom of the Florida Strait is close to zero, and hence the overall flow through the channel is less during the Gulf Stream. It's not zero, not exactly at the bottom of the Florida Strait. And there's no information here from these density slopes about how they've changed in the past. So an accurate interpretation of this is simply that the shear, the vertical of the block during glacial times was reduced. That is a fairly robust conclusion. Okay, let's up and try to get the AMOC. Going through the Florida Straits is good, but that's not the whole thing. Atlantic, because we have better data there. In the South Atlantic, it's been seen in the modern day, studied by Talley et al., that there is some coherence between the North Atlantic, at least between tropical gyres. So here, the same cores with O18 off of South America, with the black dots, and off of Africa, and draw visually a green across that. The data looks like in the modern day in A data, and we see that the water is banked up off of African margin. Channels B and C for a second. So what this looks like on the next slide. If I invert that density structure for the velocity field shown on the right, and I think that there is basically no net efflux through because we're at 30 south, and it just happens to be a special latitude. If you do a transport, that's still on the left two panels. Let's just on the far left panel, which is cumulative sum on there. You could take that as a measure of the stream function at 30 south in the South Atlantic for the modern day. And it shows strength of overturning is about a little more than 20 spheredrips, and occurs at about 1,200 meters depth. Okay, going to what we see during paleo times. Okay, so in the middle here, it's the O18 from the modern day. It shows that on the African side is generally here. That's the red line. Then O18 on the South American side, the blue line. We go social maximum, that's panel C. Now the red and blue have reversed. And if it has a density change, it would mean that we have a reversal of the shear of the AMOC during glacial times. That'd be quite if that happening. If a bit more and try to see, does O18 really correspond to density? Well, I'll turn to explain the data. And writing an AMOC reversal, what I did a study with hybrids in 2006 is that, well, let's do one panel here. It's a temperature salinity diagram. Compare basically the MI and the depth lines with the L in the solid bonds. If you make big water mass changes, and those water mass changes different African margin as compared to the South American margin, say by having import of intermediate water on one side but not the other, then we're range of temperature salinity over which we're looking, and the O18 no corresponds to density quite so well, and you really need to reverse the AMOC. Maybe a greater truth here, and that is deeper into the water column. On a temperature salinity diagram, the pignoles rotate with depth due to thermoricity, or in other words, greater compressibility of cold water. And O18 at the calcite is a good measure of density up in the ocean, but becomes progressively worse as we get deeper in the water column. Here in the South Atlantic, we were looking all the way down to 2 or 3 kilometers depth. Unfortunately, it's a very good proxy for density at those depths. Okay, so that's a method I'm taking. So let me basically participant thorium ratios, property distributions, And I'll take the next 10 minutes or so to go through that. Okay, if I should stop in 5 minutes. Okay, you protactinium-thorium ratios as being part of solving the problem of what the AMOC like in the past. With thorium, let's briefly say this, that they're both produced at a constant rate in the ocean because they are decay products of uranium, and uranium has such a long half-life in the ocean. Basically, that the production rate is uniform. The is given by the bold line in the right-hand side, 0.093, meaning protactinium is produced less than thorium. However, thorium is scavenged, or it is absorbed onto particles much more quickly than protactinium is. So, it has more time to be exported from the ocean before it gets into the sediments. If the protactinium to thorium ratio is measured to be less than the production rate, that is that there is some export of protactinium, that there is some vigorous or perhaps in the deep that is doing transport. Then protactinium nor thorium would be reported. What would be measured in the sediment is exactly the production rate. So the curve on here basically shows that curve. It's to say that about 15,000 years ago, that there's a whole lot of export of protactinium. If you take the, you can say it means that the AMOC was reduced during, say, 15,000 to 17,000 years ago. As a physical oceanographer, I would say, certainly there is a difference between AMOC strength and export of some property exported upon a integral of the property times velocity all the way across the basin, whereas the AMOC, at least if it's reduced by density on the boundaries, it really depends upon the endpoints of the basin, and it doesn't depend upon ability in the calculation. That the LGM had a reduced AMOC relative to the modern day, not just so, maybe by 30%. Okay, let's move on. So I can some of the calculus. I'll say in basically that if you more than one protactinium thorium record, they did go around the North Atlantic Ocean, and it's difficult to see how one record can have a coherent picture about the AMOC everywhere in the Atlantic. Property distributions. Here's the message from the top: is that if we go to the ocean, we have a lot more information about O18 and C18, the carbon isotope records. There are about 100 core sites in a recent compilation by Peterson and Lizicki. When input was put to this problem in years past, basically said is that it's O18 and C13, that they might have something about water masses, but run in one state that the PID data are consistent circulation rate, one the modern flux of NADW, can't get AMOC magnitude out of this. Gebbie basically said emissions were known with greater certainty, that the error bars were lower, get the AMOC out of this, but I simply don't have the data today. So instead of water masses, which don't rely upon rate constraints, and see what we say about the station in two different properties, two different sites through the Atlantic Ocean, and I pose the question of whether to tell me what circulation gives rise to this tracer distribution, and to assume that these are conservative tracers. Maybe in the top panel, a big ton of, looks like property water headed to south, but see it in the bottom panel, and you wanted to infer that one vigorous AMOC at the top, the other one does not. However, it would be incorrect because these are actually just both property distributions from the A16 line, and both come from the modern day, both from the 1990s, and they are subject to the circuit. Take is that it is only the combination of multiple properties we're able to figure out what the circulation actually was, and it probably takes 4 or 5 or 6 at least to be able to. Okay, what is well, or to be known well, about the LGM? It's, but I'm going to skip to the next one because it shows basically the same thing. This is from isotope measure, the carbon to carbon 12 ratio that goes along with the oxygen isotopes, is that appears to have been a shift in where the masses were located in the past. So carbon is shown in the top panel from the modern day. It shows deep water, basically. That it at about 2 kilometers depth going to the south. And then, at least if you get this construction that 2014 and that gives us kind of pick as Curry and Opal in 2005, it's high water, appears to hold by about 1,000 meters, and we have there above per mill at 1.5 kilometers depth. Yet a mass distribution without some change in the circulation. This is the observation of the glacial Atlantic. There and compare panels 2 and it's at the toe pattern coming from the LGM looks a lot like the cadmium record, and cadmium is a nutrient tracer. So the sense that carbon isotope records are not just a water mass tracer, but they reflect something about nutrient cycling. They're in here. It goes from water masses to the AMOC. Panel A shows, at least for the ocean, a picture holds that we have maximum southward flow in the Atlantic Ocean at 3 kilometers depth, and that is the same depth at Atlantic deep water penetrates most into the South Atlantic. I think, given different zonal patterns that aren't here in these averages, such a relationship need not hold so perfectly in the past. That's another caveat to take into account. Good. That's a good for me to move on. It shows an important point. Even masses appeared to have sold during glacial times. If you take an inverse model, what you can find is that the mass fraction of Atlantic water, that is what came from the surface of the North Atlantic, be very different during glacial times. And here I've released dye in the North Atlantic, and it goes to about the same places in the modern day, the top panel, as it does during glacial times in the bottom panel. If that is, that would lead to believe different, but not too different. The way the carbon-13 might be interpreted one way, but the solution actually wasn't that different, is the nutrient cycle. And interpreted here is that during the time there was accumulation of nutrients in the deep ocean. We're always going to have to unravel biogeochemical effects from physical effects when talking about paleo. Here's the list, I think, to tell us what the glacial AMOC was. Which is my 2014. You can water masses go, but you can also release an age tracer. And what it does for the modern day ocean is it shows low values of it, the yellow in the upper panel, just everywhere in the North Atlantic, that the north is well ventilated from North Atlantic deep water. Glacial, the ventilation is above the depth where we have a yellow tongue going to the South Atlantic. speculative, I would say, at this point, in terms of this, is that we have AMOC that has a greater southward flow above kilometers. There's still southward flow where we see North Atlantic water mass penetrating into the South Atlantic. So that would be all down to 3 or 4 kilometers depth, but then the AMOC down depth is reduced. Here, if we actually have different assumptions, plug in the Celio data, what we can find is the deep water actually may be controlled by much more than what I've shown you. So this is more traditional interpretation that paleoceanographers would have. And what it's shown is in the sighting, that's the North Atlantic deep water goes to the south. Given my first estimate I showed you, the traditional estimate is also consistent with data, and that had a hatched region, region of North Atlantic deep water in the past. So data is still ambiguous, and what to do is add data, is use more sophisticated models, and try to get data of different types to resolve this. I'll just briefly say that carbon was not used in a couple of the studies I showed you before. Radiocarbon decays, we know how fast it decays. During glacial times, it's the far right-hand side of this panel. Radioids were much lower in the deep ocean, and that's consistent with the picture I've shown you of the AMOC being reduced in the deep ocean, at least the ocean being less well ventilated. Would have to relate the North Atlantic Ocean to what's going on in the South Atlantic, what's going on in the Southern Ocean, and what's going on at the surface. Read the Furry et al. Paper in 2014 for an interesting description. Okay, take here. That's different from physical oceanography. Logs for chronometers, hydrometric measurements, density measurement, mass, age truths. However, the data is constrained to the seafloor, and we're still building towards what the AMOC was actually like during glacial times, with the most probable scenario, in my opinion, being that the AMOC strength was not too different from today, but that the function was altered such that the deep Atlantic Ocean was less well ventilated. But thanks for taking the question.
Thanks, Jay. That's great. Any questions?